Okay, so let's get started with the afternoon session. So in this session, we have invited speakers, so thank you to all the speakers for coming. And our first speaker is Idit Keidar from
Thank you. And I'm going to talk about the actually PhD work of my student Phil Barré, who just graduated last month. And this is joint work with Eddie Bortnikov from Yahoo Research, and Alexander Schreier was at Google at the time that we wrote this work. Now he's with Apple, so this is all over the place. Some of you saw the title of my talk, Composition of Coordination Services, and asked me, what do you mean by coordination services? So that's a good question. Let's get started. Coordination services. Maybe some of you have heard of Zookeeper or etcd or Doozer or Console. These are extremely popular services, libraries that run some kind of a consensus engine, basically usually based on Paxos, if you heard of Paxos. If not, now you heard the name. And they're used in distributed systems ubiquitously for storing configurations data, for electing leaders, for synchronizing locks, for storing metadata of systems and things like that. So who uses these services? If you haven't heard of them, the bottom line is that pretty much everybody uses them. And a lot of products use them directly, but you get a lot of transitive closure type of usage. So it's pretty much impossible to build a distributed system today with any open source tools without using one of these, because they're embedded in a lot of the products you're going to be using. And the motivation for this work was actually, we started working on it for the Zookeeper project at the time when Zookeeper was still more popular. Now etcd is like the new kid on the block, the biggest, the most popular one these days. Maybe you've heard of it. Okay, so what do people do with these? Basically, they're used to synchronize access to some shared data. So for example, if we have this company called FlyFast, and John connects to FlyFast and tries to see if there are any tickets available, and it learns that there is one ticket available. So John is thinking about it, maybe he wants to buy the ticket. And then Lee comes along and also checks and also learns that there's one last ticket available. And then, the usual scenario, John wants to buy the last ticket. He sends a request. This request actually goes through this coordination service that is deployed inside FlyFast. It goes through this engine. Before the ticket can be booked, it will be ordered through this service. What?
You want a laser pointer?
I have one, but it's okay. The mouse is fine too, right? Okay. And then Lee wants to buy it as well. So his request also goes through the coordination service. And the coordination service orders these requests, and therefore, once it allocates the last ticket to John, it can tell Lee that there are no more tickets available. So that's the basic usage, and it's used really for a lot of things. And here's an example of how it works inside. So the coordination service, I mentioned this before, it uses some kind of a consensus engine. So for example, a Paxos consensus protocol. So Paxos requires at least 3 servers because it needs a majority to make a decision. So to tolerate one failure, it needs 3. The client connects to one of these. And let's say we're maintaining X. X could be, the number of tickets sold, for example, for concert. And X is 0 initially. And then the client sends a request. It says set X to 5. I want to buy 5 tickets. So this request is going to go through the protocol, the consensus protocol. The consensus protocol needs a majority to decide. So two of the servers are going to be updated with a new value because they participated in the consensus. They're called the quorum that decided on this. And the third server is going to be behind. It's not going to know that the decision was to update it yet by the time the client gets its response. So if another client comes along and tries to query and to ask what is the value of X, then queries are processed locally because we want them to be fast, as in the example of FlyFast before. The clients could ask if there are tickets available and they get the response really quickly. And so it learns that there are still tickets available even though there aren't. Okay, that X is still 0 even though it is still 5. That's what these services do. So they synchronize all the updates, but they let you read stale data sometimes. So we tried to look at this a little more carefully, what the semantics of these services are. And previous papers, these are not theory papers, they're usually systems papers, and they're written very informally. And what they would say is we have linearizable or atomic sets or updates. All updates are linearizable. Linearizable means that they look like a sequential execution to everybody in this system, and that the reads are sequentially consistent. So what is the difference between sequentially consistent and linearizable? The difference is real-time order. In a sequential consistent history, things can happen in the future or in the past. So for example, I can read a value that was valid before. There already have been updates, but I'm reading in the past. So that the different processes have different timelines. That's sort of the intuition. But writing it this way, it's not really clear what it means, right? Because what does it mean that the updates are linearizable? If nobody reads them, then it doesn't really matter what the order they occur in is, right? And the reads somehow have to be synchronized with the updates. That you can't talk about their order independently of the updates because they have to read things that are updated. What we did, what these services really mean is something like this. When they say linearizable sets or linearizable updates, linearizable writes, they mean that the client see the updates in the same order. And when they say that the reads are sequentially consistent, they mean that the reads can be read from the past. So, for example, if we have two clients here, one of them is trying to set x to 3, one is trying to set x to 5. These two operations are concurrent, so we don't know which one of them happens first. Either one can happen first according to linearizability, or in general in distributed system, if two things happen at once, then either one can happen first. But the client here definitely performs the get after the first set. So should see 3 or 5 if it were linearizable, but it is allowed to see 0 here because it's allowed to read from the past. So you can read the initial state before it was set either to 3 or to 5. So that's what sort of the sequentially consistent reads intuitively means. And the
give them 0 all the time and go on.
Yeah, then you need to worry about eventual propagation, which is a different issue. But let's leave the Leibniz issue aside. So the other thing about the linearizable gets or sets is that the updates, everybody sees the updates in the same order. So if this client sees 5 before 3, then 5 must happen before 3 everywhere, and the other client must see 5 before 3. And the client might read in the past compared to the real time, but not compared to its previous writes. So client can never see something older than it saw before. So clients always move forward along this timeline of the updates. So what we did in a separate paper, not the one I'm talking about now, in an IPL paper, was formalize this and generalize this. We defined a semantics called ordered sequential consistency, which is a generalization that captures both linearizability on one hand and sequential consistency on the other hand. Both of them require that there is some order of execution that explains everything, except the linearizable requires this execution to be consistent with the real-time orders of all the processes. And for example, a read must always see the latest write. It can't read from the past. And sequential consistency allows things to move, to be a little flexible, and for processes to have their events happen after events that happen later. So OSC is parameterized and it can capture these two extremes, but the more interesting thing from our perspective is that by instantiating it with the appropriate predicate, we can get the real-time order for some operations, which is exactly what the coordination services do. They gave us the real-time order for updates, but not for reads. So reads can still happen from the past, but updates cannot happen out of order and cannot be read out of order. So why did we need to formalize this? Because we're going to try to prove that a service we implement satisfies this, and you can't prove that your service is correct without a specification, but the fact that it's a generalization, it's actually nice, and actually there's going to be, I think, a follow-up work on this that generalizes it even further. But that was an aside, so back to this work. So this work, as I told you, was done with all these people that worked on Zookeeper, at Yahoo and Google and these places. And the challenge they wanted to address is, how do I take these services? In their case, they were looking at Zookeeper, but the same question applies to the others. And how do I deploy it over WAN? Zookeeper is originally intended to run in one data center where you have the whole quorum is multiple servers residing at the same site. How do you take this service and deploy it over a wide area network if you have multiple data centers and you want this metadata managed by the service accessible from multiple data centers? Now, this was really a real problem, a real pain point for a lot of people. These are just some examples of forums over the internet and discussions about this topic, but this is really a serious problem, and that was the motivation for the work. Specifically, the motivation was in Zookeeper, even though the principles are more general. So why is it a problem to deploy a coordination service over WAN? Well, let's see how you could do this. So one thing you could do is you could say, okay, I don't want just fault tolerance, I want disaster tolerance, I want to tolerate its data center failure. So instead of 3 servers in the same data center, I'm going to have 3 data centers. And now I'm going to always tolerate a data center failure, and I'm going to deploy the whole quorum over WAN. Well, the problem is that updates are going to be very, very slow, because every update is going to have to go through a quorum in 2 data centers. And moreover, if the clients are in the 3rd data center, they will have to get their data center to the others, right? Because usually they use the same format over time. This approach was nevertheless used in Google's Megastore and a system called Zeus and in ACMS, but all these services, they didn't want high performance. They said this is very slow, but we want everything to be consistent. And with these solutions, reads are still fast. Why are reads still fast?
Everything is cache local.
Yeah, because everything is local. The reads can still be local, because the reads don't need to go through the quorum. They don't need to be consistent. They just read locally. So reads are still very fast. So these guys said, okay, we're fine with updates being very slow because the reads are still fast and everything is correct. And now we get disaster recovery, which is an advantage. But if you want higher performance for your reads, what you can do, and this is the actually recommended Zookeeper setting for wide area networks, is install something that is called in the Paxos terminology a learner. Zookeeper actually calls it an observer, and and Console calls it a proxy. Maybe proxy is the best name here. It's really a proxy. It's another server that sits at data center 2. It doesn't participate in the quorum, in the consensus votes, but it proxies for it. So the updates are sort of propagated to this learner, and the clients can see it locally. And if the client wants to do an update, it goes to the learner forwards it, proxies it for the client, forwards it to the data center, and then the data center runs the consensus protocol, agrees on it, and sends it back to the learner. So with this solution, the updates are a little faster. They're still slow for the clients in data center 2 because everything goes remotely, but not as slow as before. And as I said before, this is the recommended solution. It's widely used. But what if we have a lot of local data that the clients in data center 2 use heavily, and they don't want to have to go to data center 1 every time they want to access it? Well, in this case, some people tried, and if you look at forums over the internet, were kind of trying this deployment and wondering what would happen, is to just say, okay, then we'll have the data that's mostly used by clients of data center 2, we'll manage it in data center 2, and the data that's mostly used by clients in data center 1, we'll manage it by a completely independent Zookeeper instance, completely independent coordination service instance in data center 1. And then we'll have learners or proxies for both data centers for each other. This is here, the updates are as fast as when the single Zookeeper because they're local. They still require a quorum, but they're local to the local data center. The reads are still fast. as before, but there is a problem that this is not correct. And what do we mean by correct? That's why I gave you the definition before. Well, I didn't give the formal one, but the intuition for the definition before. And the thing about this definition, and also about sequential consistency, is that it's not composable. So if we take two objects, one manager DC1 and one at DC2, each of them satisfies the semantics that we want. Together, they won't satisfy the two semantics because it's not composable. The composition will not be correct. Why does that happen? So here's an example. So we have these two objects. X is managed by one cloud, one Zookeeper. Y is managed by etcd, another cloud, some other service. And now the clients try to access them. So we know that reads can be served from the past. So if we have client 2 updating X to 0, client 1 updating X to 5, we can still have a later client 2 read X is equal to 0. So we can have this order, that this read is before this write. Okay? And if client 2 before reading 0 from X wrote to the other object, to Y, then we have this relationship because the client's operations must appear in order. And on the other hand, if client 1 now decides to read Y, it can still see 0 because it's allowed to read from the past. That's what the etcd instance that maintains Y allows it to do. Okay? And as you can see, we get client C the updates in a different order. From the perspective of client 2, the update of Y happens first, and then the update of X. And from client 1, the update of X happens first, and then the update of Y. So if both X and Y were managed by the same coordination service, this wouldn't happen. Okay? They would be consistent. We wouldn't get this violation of consistency. This is because we compose two services that don't know of each other, and each one of them was correct by itself, but their composition is not correct. So what do we do about it? What we do is we add a thin composition layer between the client and the data center and the service that ensures that the composition is going to be correct. Okay, it's a very thin client-side library. It sits between the client and the server, captures the client's communication outside to the server, and it ensures the composition is correct. Okay, I'm going to say what we do in a minute, but by this approach, we get a solution where the updates are fast, assuming there is locality. If there is no locality, they're not going to be fast. The reads are fast. That's true with all the solutions, and we get the correctness. So now we get that it's correct. Okay, so how do we do this? How do we make this modular composition? Well, we observe. So let's first of all think what we could do. You know, if we wanted a solution that was always correct and without worrying about performance, what we could do is we could take the reads and pipe them through the quorum as well. If we took the reads and sent them through the quorum, then we would get linearizability. Okay, the difference between sequential consistency. The reason why we get sequential consistency and not linearizability is because we allow the reads to be local, so they can read from the past. But if we would send them through the quorum, they would be linearizable, and linearizability is well known to be composable. So the composition is correct. So we'd have two linearizable surfaces, their composition would be correct. But we don't want to pay that much. We don't want to make reads slow as the writes. We want reads to still be able to read from a single copy. But sometimes, only sometimes, we're going to make them slow. So we're going to take reads, whenever the read accesses a different service instance, a variable that sits at a different Zookeeper than their previous access, and if that access is a read, we're going to add a dummy update operation before that in order to force it to synchronize. That dummy operation is called a sync. Okay, how does this work? So if we have the client here, this is the example that I showed before. The client sets Y to 3 and then it reads X. But before reading X, because X is managed by a different instance, different cloud, different provider than Y, it will invoke this dummy operation, sync, on X, on the new service. Okay, so whenever you start accessing a new service, you have to start with an update. So in this case, because it wanted to start with the read, we had a dummy update. Well, this sync still allows it to read from, if after adding the sync, it still reads 0, we know that this sync cannot follow, completely follow the set of 5. Okay, before we saw this example where client 1 sets it to 5. Well, if this sync would happen after this set, then it would, the get here would be 5. So by the fact that the get here returns 0, we know that these two are concurrent. Okay, and that the linear, the coordination service of X ordered this one before this one. So why does it help us? This is the line that showed that they overlap. This means that the sync that client 1 will do before accessing Y will have to be strictly after the set of Y to 3. Okay, that's because this, it strictly follows an operation that overlaps the operation that strictly follows this one. That's what we see in this line. So now this get cannot return 0 anymore because it happens after the sync, then it happens after the set. So it reads from the sync. So we kind of flushed it and forced it to read from a later point. We don't let it, it can't go as further back in time than the last sync that it did. And here the clients see the same order of updates. They don't see conflicting updates. Okay, so here everybody sees the update of Y happening before the update of X. So the formal proof that this this property makes the composition of OSC objects in general correct is in the IPL paper. And I'll just show now the 10 minutes. Okay. So now I'm going to show some results about the evaluation. This is I probably forgot to say this. This was on the first slide. This is a Usenix ATC paper. So it's kind of it's a systems paper. So I'm going to show now the evaluation results, the numbers. So this is one. Oh, sorry for the numbers. So this is an example of how our implementation of ZooNet is. ZooNet is a library we implemented that adds on to Zookeeper, and this is an illustration of how ZooNet composes coordination services. So if we have a legacy client connecting to the coordination services, so wants to invoke an operation, you just invoke the usual operations. We don't change it. If we want the ZooNet-enabled client, then the client will run ZooNet, this sort of thin layer between the coordination the client and the service. And the client will be aware of the fact that it has multiple namespaces now that it connects to. So, for example, instead of just calling get AB, it will know that it works from multiple data centers. So it will say, I want AB from data center 2. And the ZooNet library is going to strip this data set DC2 prefix and call get on /A/B. It's going to work alongside the legacy client as before. And if the client wants to get information, some data from DC1, which is the other data center, then ZooNet will also strip DC1, send this request to the learner instead of the original of the local data center to the local proxy for the remote data center. But as you can see in this example, this is the first invocation of an operation on DC1, so it has to be an update operation because it is not. We had a sync here. So when the client does this, this is what's going to happen. The sync is going to be sent here, and then the get /C/D is going to happen. The sync is going to flush the pipe, and then the get is going to read the new state. If there be subsequent gets to DC1, they will not invoke sync again. Okay, so now for the evaluation. So this is the setting of the first evaluation. We have two sets of experiments. The first set of experiments, we just want to see what is the cost of getting this consistency. So we have this Zookeeper deployment with the addition of ZooNet. Okay, we have this data center and the remote data center and ZooNet, and we want to see this is the inconsistent deployment and this is the consistent deployment. We want to see what is the cost of consistency. So as I mentioned before, one way we could ensure consistency was to do everything atomic, including the reads. And that's when we get this red curve that is slow because all the updates are atomic, but also all the reads are atomic. So all the reads have to go through the core. Okay, this graph, this graph shows the scenario of 100% spatial locality, meaning that every client accesses only data in its local data center. So we are supporting the existence of another data center. We do have the ZooNet library here. It does know to do things, but we're not using it. This is just to see if we had any overhead to the regular operations. So all the accesses by this client are to DC2. Okay? So the inconsistent implementation, actually it turns out to be correct in this case because it only accesses one data center, but it gets faster as we have more reads. Because when we have updates, we have to send them through the quorum, and then as we have reads, we become a lot faster than sending reads through the quorum. And in this case, not surprisingly, ZooNet is exactly the same as the inconsistent version because we don't do any synchronization. Okay, it just doesn't do anything. It doesn't add any overhead. Okay, so that's good. Now let's see what happens when we vary the locality. So in this example, we assume there is no temporal locality. What does that mean? It means that every time the client invokes a new operation, it flips the coin to decide whether to go to DC1 or to DC2. There's no locality. It doesn't access 10 fields in a row in one directory. Okay, this is not a very realistic scenario, but just to see what happens, we look at this extreme case, but we vary the spatial locality. So along the x-axis. So at the right-hand side, all the accesses are local, and the left-hand side, half the accesses are local for the clients in DC2. And what we see is that if we look at read-only performance, then we get the same graph that we saw before, pretty much. The more, when we have local, only local accesses, then ZooNet and the inconsistent version are the same. And when we have a lot of, when we have half the accesses and half are local, then we are slower. And in the left-hand side, we have a scenario which is 50% read and 50% write. And there's something a little quirky about this graph because we have these peaks that it kind of seems like it should be improving the more local we get, but it's because we ran these experiments by saturating the servers and we try to get the peak throughput, then actually at some point the local quorum becomes saturated and we actually benefit by offloading some of the requests to the remote quorum. That's why we get these peaks. So at 100% local, we only have the resources of one quorum, and for example, here at 90% local, we have resources of other quorums. So what we see here is that as we have more locality, we benefit more from ZooNet, and we don't have locality, we don't benefit from it. This is not so surprising. Okay, that's about the spatial locality. And then if we add temporal locality, which is very common. So for example, if an application accesses some data, it usually would access the directory, traverse the directory, maybe look at some files. So it would make many requests to the same service. So if we do have temporal locality, it doesn't really matter whether we have spatial locality or not. In all cases, Zookeeper is as fast, ZooNet is as fast as the inconsistent version. Why is that? Why does that happen? No? Anyone? This is because of amortization, right? We only send the sync when we switch a coordination service. If we do 10 requests in a row on the same coordination service, we only do this 1 in 10. So it gets amortized. So we don't, the cost is amortized, the benefit is maximized. Okay. Just one more scenario. The second scenario we do is we take the recommended Zookeeper implementation of all only an observer and compare it to the ZooNet implementation. And here too, what we see in this graph is the speed up of ZooNet over Zookeeper, and here we see that the more local data the clients in the data center access, the more they benefit from having their own coordination service instance. It's not surprising, but we do get pretty high here. It's keeping me confined to this space the whole talk. Like, okay, fine. So it's really significant if we have a lot of local updates. We could go as much as 7 times faster just by having a local quorum and not having to go over WAN for everything. And this weird peak here, remember why it is? Same as before. Okay, because we offload. Because when here the quorum is saturated, here we benefit from doing some things remotely. Okay, so that's just a Zookeeper versus ZooNet evaluation. I don't have more time, right? I do? Okay. So just as an aside, this is not part of what I'm talking about, but as we came to build this service, we saw a serious problem in Zookeeper where clients we used to block each other. So if you took 2 clients and connected them to the same server, and one of them was doing updates and the other was just a read-only, then the client doing the updates would block the read-only client. The semantics doesn't require it, but it was just that way in the implementation. So Kfir, my student, he actually fixed this, ran all the complex system tests that the open source community defined for Zookeeper, committed, and Alex, which is also co-author of this, who is also co-author of this paper, is a committer for Zookeeper. So they committed into Zookeeper, so now this improvement actually works in Zookeeper, and you can see the details online. Just as an cool aside, and this improves performance significantly, and if we wouldn't have done that, then all of our experiments would be kind of meaningless, because we would be comparing a good version to a very, very, very slow version. So now we compare a good version to an improved version, 10 times faster version. Okay, so to conclude, we gave a modular approach to composing coordination services that has good performance, is simple. It has good performance at least if there's locality, either spatial or temporal. It's very simple, and we proved that it's correct in a separate paper. It's a very small change on the client side. There's no changes on the server side. That was like the Zookeeper improvement that we did independently. It's backwards compatible, so it works with legacy clients. And yeah, the higher the locality is, the lower the cost. And on the side, we improved Zookeeper by 10%, 10x, but that's kind of independent. So thank you.